Okay, so systems of equations is something that you did in Algebra 1. What we're supposed to do are more complicated systems of equations. You did linear systems. We're supposed to be doing nonlinear systems. What I find is that most students, once they get beyond Algebra 1, really don't remember that much about systems. So we're going to go back and do the linear stuff, and then we'll add a little bit. It's really not that much. I mean, if we were like really rushed, we'd make one day out of nonlinear systems and be done with it, you know. But we have the time to do this. So, you know, you copied for that extra credit homework. First, what it looks like when you've got a linear system, and then some possibilities for what does it look like when you have nonlinear systems. Now, really, we're not so interested in all nonlinear systems. We're interested in quadratic systems, right? And at this point, there's only one kind of quadratic function that we've dealt with, right? And that's the one that had a graph, which was a parabola. But in fact, they don't have to be parabolas. They can be ellipses, circles, hyperbolas, right? All of those are the result of graphing quadratic equations. And, you know, they can all be things that we end up solving, you know, by the time we're done with this. Okay, let's see. So, system of equations, just to refresh your memory. A system of equations is more than one equation with more than one variable. Generally, you know, 2 equations with 2 variables, 3 equations with 3 variables, right? As long as you have the same number of equations as variables, usually you can solve it. You know, there's a system of equations that we use in meteorology to model the atmosphere. That's called the primitive equations. That's 7 equations and 7 variables. And they're not linear equations, right? They're partial differential equations that actually, you know, have time as an independent variable. So everything that you put into it, pressure and temperature and 3 components of wind, all of that is changing with time too, right? But still, we're using the same kind of stuff and then trying to push this stuff out in time. Make a forecast. Right? The solution to a system is the set of all the points that satisfy every equation in the system. You plug it in every one, you'd plug it in and it would check, 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 check. For a 2 by 2, meaning 2 equations and 2 variables, both equations are linear. The solution, if it exists, is the intersection of their lines. You would graph the lines, look for the intersection point, there's your answer. So there's 3 possibilities for a 2 by 2. This stuff you've seen before, it's what you copied in the notes, right? So one possibility is that 2 lines intersect at a point. So the solution would be whatever the coordinates of that point are right there. So if 2 lines are going to intersect, it's got to be because their slopes aren't equal. Anytime slopes are not equal, that means these lines are going to intersect. They're going to intersect at one point. Forget it. Okay, what would it be like what would the lines be like if there was no solution? Yeah, they'd have to be parallel. See if I can get it to change this time. I'll try to make those parallel. There we go. Right, parallel lines never intersect, So there's no solution. There's no point that can be on both lines if they never cross. So we know that parallel lines have the same slope, right? M1 equals M2, right? They got to have different y-intercepts. What if they had the same slope and the same y-intercept? It'd be the same line, right? That would be this situation here. Right? When both lines have the same slope and the same y-intercept, then they are the same line. Trying to draw those like right on top of each other. It doesn't mean that there's no solution. It means there's infinitely many solutions, right? Every point that's on one line is necessarily on the other line. You already copied most of that anyway. So these are our methods for solving linear systems. We're going to go over the first two today, right, with linear systems. And then the next class we'll do elimination for linear systems. Then we're going to look at how you can use the calculator to actually graph these and solve. And then we're going to spread it to nonlinear systems. We're not going to do matrices, but that is a method you could use. I don't think there's anywhere in our curriculum now that we actually teach matrices. It used to be part of the curriculum, so it was a little more natural to use that as a way to solve systems of equations. Let me write that in there. So this is today. So solve by graphing. So here's two linear equations. Graph them. How would you graph those lines if I asked you to graph them, if your life depended on it? Solve for y. Okay, you could definitely do that. You know, if you solve the first one for y, you would get y equals negative 4x plus 8. Okay. If I solve the second one for y, then it looks like I would get y equals 2/3 x minus 6. And then you could graph them in slope-intercept, right? By doing the y-intercept and then using the slope. Remember, another thing you can do is when you're given a line that's in standard form, it's actually easier to graph by just finding the x and the y-intercept. Right? The x-intercept, where it crosses the x-axis, also known as a 0, is what you get when you plug in y equals 0. So that's just like cover up the y, 4x equals 8, so x equals 2. Right? So I can graph that point. And then if I did the same thing, if I want to find the y-intercept, then I substitute x equals 0, so y equals 8. And I'm a little off the chart, but I'll just put it up there. So those 2 points are enough for me to define where that line is. So let me do that. See if I can make this look right. That's pretty good. Was at the end, it just, okay, there you go. Okay, now let's do the other one. The other one I'll do with slope-intercept form. Y equals 2/3 x minus 6, so first there, and then 2/3 means up 2, right 3. Hopefully this is something you know. right? So there's 2 points. Connect them with a line. And it doesn't much matter because I can see. Where is the solution? Yeah. I mean, it looks like, from my graph, it looks like it's the point 3, -4, right? So I can estimate that, 3, -4. Now, how could I be sure if that's right? You could plug it in and see whether it checks. You know, you could plug it into the equations on the top, or you could plug it in the 2 that we solved for y. You know, if I do the one up here, 4 times 3 will be 12, plus -4 is 8. That checks. This one is 2 times 3 is 6, sorry, 6. Minus 3 times -4 is like plus 12. So that's good too. Right. So what you can see is that when you solve by graphing, it really has to do, if you're graphing by hand, it has to do with how accurate is your graph. You know, if you're drawing, you know, without a ruler, without all the tools like that, you might get close, but you're not likely to get exact. So try to do this one. See how accurate you could be graphing these by hand and estimating the solution. Right, if you solve them for y and then you graph, right, the first one should have been 4/5 x plus 2. So the y-intercept is here, up 4, 1, 2, 3, 4, over 5. The second one, -4/7, which puts it about in between 0 and -1, but maybe there. And you're going to go up 2 and over 7. So up 2 over 7. Draw a line. So that's the solution right there. And you can estimate the point. Right? What are the coordinates of that point? -5, -2. But you know what? I knew the answer before I started, so I was kind of making sure they got close. Last block, I was off. So, I mean, that's always the thing. If you're going to solve by graphing, you know, you're not going to be exact unless you do it with a calculator, and we'll learn that later. You know, what we're a little more interested in now is how do we solve it exactly, right? And the first algebraic method that we've got is substitution. Here we go. Solve by substitution. First step said solve one equation for one variable. Which variable, which equation? Yeah, in the end, it does not matter. You could pick any one you want, but there's an obvious choice here, right? If you solve the second equation for x, then you're not going to be making fractions that'll make it harder to solve. If I solve for x here or either of the y's there, the last step I'm dividing by something that's going to make fractions, which will make it harder. So, I mean, you can solve anything you want, but the reason that I put a problem which has got one variable, which is just 1 times x, is because that's probably where you want to start. Okay, so first step would be solve that. Let me get back to blue. So this is x equals 3 minus 3y. Okay, second step. Substitute for that variable in the other equation, right? Don't substitute into the same place that you just took it. That's not good, right? Substitute it for the x in the other equation there. Okay. So that'll look like this. 2 times 3 minus 3y plus 5y equals -5. Right, can you see I just replaced the x with 3y minus 3 minus 3y. So by doing that, we reduced what was a 2-by-2 system of equations into one equation with one variable that could be solved pretty easily. So that'll be 6 minus 6y plus 5y equals negative 5. Combine like terms, 6 minus y equals negative 5. Subtract 6 and multiply by negative 1. So y is 11. Bad y. Okay, that's the end of step 2, right? Step 3 is substitute that answer into the equation that you solved for step 1, right? This one right here. So put in y equals 11 there. X equals 3 minus 3 times 11. X equals 3 minus 33. X equals negative 30. Right. So the answer to this, the solution to this system is negative 30, comma 11. Right. That's a point. Good. Okay. So try this one. Solve by substitution. See if you can get it. I'm just going to do it in one step. X equals 2y plus 3. Now substitute into this equation. Negative 4 times 2y plus 3 plus 7y equals negative 16. Negative 8y minus 12 plus 7y is negative 16. Negative 8y plus 7y is negative y minus 12 is negative 16. Add 12. Negative y equals negative 4, so y equals 4. And then I come up here and say x equals 2 times 4 plus 3. 11, comma 4. Good. Okay, now I'm going to solve this one by substitution. Okay. Which equation am I going to solve for which variable? Probably the first one, right? So x equals 2y plus 4. Now I'm going to substitute into the other equation for x. 3 times 2y plus 4 minus 6y equals 8. 6y plus 12 minus 6y equals 8. The 6y's cancel. So all that I'm left with is 12 equals 8. What does it usually mean when we're solving something and we get something like that? There's no solution. Okay, so what does that tell you about those two lines? They're parallel. They never touch, right? So there is no intersection point. So we've done something that eliminated all the variables, which means the solution doesn't depend on the variables. It's either always true or it's always false. And this is false, right? Since this is false, therefore parallel lines no solution. You know, if you're solving this on a test and you get down to this point here, you've done everything correct. Make sure you say, you know, what does that mean? Don't just walk away from it. You know, you could say parallel lines or no solution, but something, you know, don't just leave it. That's wrong. Okay, how about this one? Solve by substitution. So y equals 4x plus 3. Substitute into the other equation. 12x minus 3 times 4x plus 3 equals negative 9. Yeah, thank you. So that's 12x minus 12x minus 9 equals negative 9. And again, we see that our variable terms cancel. But what's left is actually true. Right, that means that it doesn't depend on the variables. I mean, it's kind of hard to say it's always true. It's not like you could plug in anything for x and y. But every value of x will be represented here, right? And every value of y. So when you see this, right, this is a true statement that doesn't depend on the variables, right? Then it's the same line. There's infinitely many solutions. Sometimes, and I don't know whether this book does it, when you go to the back of the book and you look for your answer, they don't just say same line and walk away from it. They might use this kind of set notation and say, this is the set of all points, x, y, right, such that can either be a colon or a bar, such that the points are of the form x, comma, 4x plus 3. Right? Because we know this right here is telling us how you would find the y if you knew the x. So there's infinitely many points that will have that form. But that's what it looks like. You get a true statement like negative 9 equals negative 9. So try that one. That one's going to be one of the two, right? Either it's going to be no solution or it's going to be same line. Same line, right? If you solve this one for x, and you plug in here, and then simplify. 20 equals 20, same line. Okay, one more, and then we're done. Try that one. So should have got something like that. I solved up here, plugged it in, simplified. And if you solve an equation, like in this step here, if I solve for x, right, and then I plug that exact thing back in for x right here and simplify, it'll make it look like it's the same line, right? That'll happen whether or not it's really should be intersecting at a point or not, right? If you plug into the same equation you just solved, it's going to make it look like the same line. So that's, make sure you're careful about that. I mean, we don't make that mistake very often anyways. Okay, that's a refresher. I'm sure you all remember everything about that, right? And these dates are wrong. I think I changed it on the first slide. That should have been 226-29. This should be 334. Homework.